Today, I sent out a little worksheet with 4 problems on it that once again I chose carefully in order of difficulty. But before we could tackle that, I've been told that a lot of schools haven't done the equilibrium constant yet, so I'll do a little bit of introduction so that people can understand what the equilibrium constant is, and then we'll do some problem solving involving the equilibrium constant. So in order to understand the context of the equilibrium constant, we're going to have to go a little bit back and start with the concept of a reversible reaction. And a reversible reaction is a reaction where reactants are making products at the same time that products make reactants. So I did a little equation over there showing that on the left hand side I have reactants, and reactants make products, and then I did a simple example, the example that most teachers quite often use, which is the Haber process. And then I also indicated what is the forward reaction. The forward reaction is reactants making products, and the reverse reaction is products making reactants. So both these reactions are happening at the same time. So at the same time that nitrogen and hydrogen forms ammonia, ammonia decomposes and forms nitrogen and hydrogen. Right, so knowing that a reaction can be reversible, in fact most reactions in nature are reversible, but I want to introduce a concept called chemical equilibrium. And that happens when the rate of the forward reaction is equal to the rate of the reverse reaction. What that means is that the nitrogen and hydrogen is making ammonia just as fast as the ammonia is breaking up to form nitrogen and hydrogen. So the forward reaction, which is the reactants making products, is happening just as fast as the reaction that products are making reactants. And why is it called equilibrium? Just think this through. Just as fast as I'm making ammonia, I am using ammonia. Just as fast as I'm using nitrogen and hydrogen, I am making nitrogen and hydrogen. So the obvious conclusion to draw there is that once I've reached this state of chemical equilibrium, the concentration of the nitrogen, the concentration of the hydrogen, the concentration of the ammonia remains constant. So our first conclusion about chemical equilibrium is the concentrations of all reactants and products remain constant. Right, we must not confuse that with, I'm not saying that the concentration of nitrogen is equal to the concentration of the hydrogen is equal to the concentration of the ammonia. I'm not saying that. I'm saying that the concentration of the nitrogen remains constant. And the concentration of the hydrogen could be a different value, but that value stays constant. The concentration of the ammonia could be a different value, and that value also stays constant. So that is our first comment. We also know, obviously, that the rate of the forward reaction is equal to the rate of the reverse reaction. Right, so in order for an equilibrium to exist, 2 conditions need to be met. So in order for an equilibrium to exist, there are conditions for chemical equilibrium. And the one condition is the reaction must be reversible. It's pretty obvious because if the reaction is not reversible, then there can't be a reverse reaction. And the second condition is it must be a closed system. So what does that mean? That means that specifically because in lots of reactions we deal with gases, it must be a closed system. Now, none of the gases should be allowed to escape the system, because if the gases escape the system, they cannot partake in either a forward or a reverse reaction. So those are the two conditions for chemical equilibrium. So now we understand there's a chemical equilibrium. We understand that chemical equilibrium can exist because some reactions are reversible. Right, so that poses a problem to chemical engineers. So chemical engineers, so let's look at this Haber process quickly. So chemical engineers has the job of setting up conditions and systems to produce particular chemicals. So here's the Haber process. And the Haber process is there to manufacture ammonia. Okay? So it's a reversible reaction. So I've got to set the conditions to have a high yield of ammonia. Because if I'm not making a lot of ammonia, then what's the point? The company needs to make money because it's a business. The business needs to make money, so I must make a high as possible yield of ammonia. And the only way I can have that is that once I've reached chemical equilibrium, where the rate of the forward and the rate of the reverse reaction is the same, then I must have a high concentration of ammonia. Okay? I must have a high concentration of ammonia. Now, this, for example, is an exothermic reaction. So the Haber process is an exothermic reaction. So, and one of the most important things that I need to tell you about our chemical equilibrium is that different equilibria exists at different temperatures. And we're going to get back to that. So I want a high yield of ammonia. The problem is, if this is an exothermic reaction, then theoretically I'm producing heat. Okay? So what we see in this reaction is that the forward reaction is producing heat and the reverse reaction is using heat. Okay? So theoretically I want to have this reaction take place at a low temperature, because at a low temperature the reverse reaction is not happening efficiently because there's not enough heat for the reverse reaction to take place. So theoretically I want a low temperature for this reaction. The problem that I have with that is that if I look at our theory about rates of reactions, we notice that temperature is one of the main factors that affects the rate of a chemical reaction. At a high temperature, I would have a high rate of reaction. And at a low temperature, I would have a low rate of reaction. So at a low temperature, for example, I would make a lot of ammonia because the forward reaction doesn't need heat, but the reverse reaction needs heat, so the reverse reaction is not happening as it should. So I would have a lot of ammonia. However, I can have a high yield of ammonia, but it's going to take me a long time, because at low temperatures, everything happens slowly. So I would rather have a a more moderate yield, for example, let's say for example, I produce 80% ammonia. But my 80% ammonia, which is a high yield, takes me 9 hours to achieve. However, if I have it at a higher temperature, I could get a 70% yield in 2 hours. So as a chemical engineer, I have to make the decision about how much heat I need to use so that I can make as much ammonia as possible in as short a time as possible. So that is my job as a chemical engineer. So, in order to help me do that job, right, we as chemists have calculated different equilibrium constant values. Equilibrium constant. And that's what we want to talk about, the equilibrium constant. So what is the equilibrium constant? How is it going to help the chemical engineer on site? The equilibrium constant looks at the product, and when I use the word product over here, I'm not using the word product in the chemical sense, I'm using the word product in the mathematical sense where product means multiplication. The product of the concentration of the products, and in this case when I use the word products, I'm using it as the chemicals produced by the reactants, divided by the product of the concentrations of the reactants. So note, the equilibrium constant is the product of the concentration of the products divided by the product of the concentration of the reactants. And we're going to give that a short name, we're going to give it a name Kc. Right, so let's look at our equation again. Nitrogen plus 3H2 goes to 2NH3. Right. So what are my reactants? What are my products? So my reactants are N2, and this is 3H2. In other words, that is H2 plus H2 plus H2, and that gives me NH3 plus NH3. So these are my reactants, and these are my products. Right, so let's use that equation and write an expression called the equilibrium expression for this particular reaction. So if I look at the product of the concentration of the products, okay, so my products are NH3, that is the concentration, square brackets denotes concentration, times the concentration of NH3, because I've got two products, NH3 and NH3, and the product of the two, divided by the concentration of the N2 times the concentration of the H2 times the concentration of the H2 times the concentration of the H2. So this expression as written here, this, right, is called the equilibrium expression. And I can simplify the equilibrium expression. If I simplify that, and I know a little bit of mathematics, then I can write that as the concentration of the NH3 squared divided by the concentration of the N2 times the concentration of the H2 cube. And that would be my Kc. So what is the point of that? If I look at it, I'm basically looking at how much products do I have at equilibrium in relation to reactants. How much products do I have at equilibrium in relation to reactants? So if I've set up an equation and I've set up a chemical system to produce ammonia in this case, ammonia being my product, the thing my company manufactures as a chemical engineer, my company manufactures to make money and to pay workers and so on. I want to have a high value. I want to have more products than I have reactants. Right? So a good chemical engineer would want a high Kc value. And obviously, if Kc is greater than 1, then there's more products than reactants. Right. So that is the Kc expression. And what they've done is they've actually logged quite a few values of different reactions for Kc in a little book. So an engineer would walk around with a little book and he would look at, the Kc values at different temperatures and different pressures. So this is the equilibrium expression that we're going to use to calculate Kc values for different reactions. And these Kc values are temperature specific. In other words, they are different at different temperatures. They are different at different temperatures. Thus, temperature, I'm saying this in as many ways as possible, affects the value of the equilibrium constant. And I decided to do a lesson on the equilibrium constant today because you will notice that if you pick up second papers, there are lots and lots of questions. I mean, every second paper has a Kc calculation in it, and they are quite often between 7 and 10 marks. And those are significant amount of marks in an examination paper. And so I've given you an idea of how to set up the equilibrium expression, and I've given you an idea of why there's an equilibrium Kc value, and also that it's temperature specific. I've given you the conditions for equilibrium, etc. So what I did was I sent out a little worksheet with 4 problems on it, and we're going to tackle those problems. Okay? The worksheet is the following worksheet that I sent to your school. And we're going to tackle this, and we're going to set up the solutions to this questions. Right, so I'm going to read the question, set it up, show you how I tackle it, give you some advice, and then we will look at the second one and we'll go on from there. So, 0.5 moles of hydrogen gas and 0.5 moles of oxygen gas are sealed in a 200 centimeter cube container at a temperature of 118 degrees Celsius. Notice the temperature is mentioned because the Kc value that we're going to calculate is specific to that temperature. The following chemical equilibrium is established after a certain time. Notice that all the reactants and products are gases. Such a reaction right, is called a homogeneous reaction. Okay? And that means that all reactants and products are in the same phase. All reactants and products are in the same phase. Notice they are all gases. That's a gas, and that's a gas. Right? So, if one of those is a solid or liquid, then they're not all in the same phase. Right? So when all reactants and products are not in the same phase, the opposite of homogeneous is heterogeneous. And that would mean that all the reactants and products are not in the same phase. Right, so let's get back to the problem. Analysis of the equilibrium mixture shows that the mass of oxygen in the container is 9,6 grams. Calculate the equilibrium constant for the reaction at this temperature. So what we're going to do is we're going to set up a table. Okay? So when I solve this problem, the first thing that I do is I write down my equation. Nitrogen plus hydrogen gives me ammonia, and I put my balancing numbers in. And the reason why I put my balancing numbers in is my balancing numbers gives me the mole ratio. So the mole ratio is 1 is to 3 is to 2. That means that 1 mole of nitrogen uses 3 moles of hydrogen and produces 2 moles of ammonia. Okay? And then I set up my equation, my table. And I start with the moles at start. So at the start of the reaction, there's a certain amount of moles of certain things. Then I've got a column that says plus minus. Some of you might use the word change. I use plus minus, it will become obvious afterwards. Then I use moles at equilibrium. And then I go concentration at equilibrium. And I make those 4 rows. Okay. Let's make those bigger. I think I've confused the reaction with the previous reaction. Let me just double check my reaction so I can fix that up. My reaction was hydrogen plus oxygen gives me water. Let me just fix that up. We have H2 plus O2 gives me 2 waters. Right. And my mole ratio in this case is 1 is to 1 is to 2. Right. So there's my table. Okay. So what I do, especially when learners are starting to learn how to use the table and how to understand the table, I use color coding. So everything that is given, for example, the 0,5 moles of oxygen, the 0,5 moles of hydrogen, and the 9,6 grams of oxygen that is left over, that is information that is given. So when I go back to the table, and I put in that is the column for hydrogen, that is the column for oxygen, and that is the column for water. Then what I do is I write those values in red. So in red is all the information that is given to me. So, and I read again, and I remind you, 0.5 moles of hydrogen gas and 0.5 moles of oxygen gas are sealed in a 200 decimeter cube container. There's no water there yet. Okay? So at the start, there is 0 water. And that is given to us. Right. Then it says that at equilibrium, analysis at equilibrium. I think I jumped. No? Where is nothing? Right. Analysis at equilibrium shows that there's 9.6 grams of oxygen in the container. Now, my table doesn't show grams. My table shows moles. And of course, moles is equal to mass divided by molar mass. And 9.6 grams divided by the molar mass. It's O2. So it's 16 plus 16 is 32. And that gives me, on the calculator, I think it's 0.3 moles. Right, so if we are given grams, we turn it to moles and then we can use it in our table. So the other piece of information that was given was that the oxygen at equilibrium was 0.3. And that is all written in red. Okay, so it is at this stage that I've put in all the information. I go to the column where I have 2 pieces of information. And in that column, I noticed I had 0.5 moles of oxygen. I had 0.5 moles of oxygen. And after I've reached equilibrium, I have 0.3 moles of oxygen. Oxygen is a reactant. Right? So I used oxygen. Right? I used oxygen. So in green, I must have used 0.2 moles. Because I had 0.5, I used 0.2, I now have 0.3 left over. And in that column where I've written the green, this is where I use my mole ratio. And my mole ratio says that if I use 2 moles of hydrogen, I use 1 mole of oxygen. So obviously if I use 0.2 moles of oxygen, I must have used 0.4 moles of hydrogen. And the ratio obviously says that ratio is 2:2 or 1:2 over there, whichever one I want to compare, I must have made 0.4 moles of water. Right, so the minus actually means I used it, and the plus means that I produced. Okay, so now we look at our columns and we see I had 0.5 moles of hydrogen at the start. I used 0.4, and that means I have 0.1 moles left over. If I go down to oxygen again, I have 0.5, I use 0.2, and I have 0.3 moles left over. At the start, I had no water. I produced 0.4. So at equilibrium, I now have 0.4 moles. So those are the moles at equilibrium. Now, I remind you that our equilibrium expression is about concentrations. And I go back and I look at my volume. And my volume is 200 centimeters cubed. And since concentration is moles over volume, if I start with the water, right, I've got 0,4 moles, and 200 centimeters cubed is 0,2 decimeters cubed, so I have 2 moles. 2 moles per decimeter cubed. So the concentration of water is 2 moles per decimeter cubed. The concentration of oxygen is 0,3 divided by 0,2, and that gives me 1,5. The concentration of hydrogen, that's the concentration of hydrogen is 0,1 divided by 0,2, and that gives me 0,5. Right, so now I can fill those in, that is 1,5, and that is 0,5. And those are my concentrations. Right, so now I can find out what my equilibrium constant is. And my equilibrium constant Kc is equal to, remember, it's the product of the products, so it's H2O, and remember that 2 there means there are 2 of those, and if I simplify, that would be a square. There's 2 hydrogens, so that's H2, that is a square. There's only 1 oxygen, so that is that. So, the Kc calculation. Concentration of the water, that is 2 squared, divided by concentration of the hydrogen, 0,5 squared, multiplied by 1,5. And we work that out. And remember, Kc does not have units. Just taking out my calculator, and I go and I calculate 2 squared divided by 0,5 squared times 1,5 equals, and we get an answer of 10,67. So as a chemical engineer, I'm very proud of myself. I've got a very high Kc value. I'm producing product. In this case, my product is water, and I'm satisfied with that value. Okay, so let's have a look again. We're looking at the whole solution. Notice, when you look at it now, you can actually see what was the information given. It's all in red. You can actually see where the ratio was applied, and we look at that ratio, we look at the mole ratio in the equation. It is quite clear that that mole ratio was correct. Okay, and then the rest of the calculations I do in blue or black, whichever color we're writing in, and then we set up our equilibrium expression, plug in the values of our concentrations that we got from the table, and we go from there. Okay, so let's see if I'm going to give you a few minutes to set up the table, right, and see if you can use the information that was given, right, and the method that was given to set up a table, right, and go firstly just as far as filling in all the information that is required. So all I want you to do now is to set up the table and then fill in all the information that is given in the problem. So as a learner, set up the table for me, use the values, set it up, put it in. If there's grams given, convert it to moles, and then see. And then stop there, and then I'll go to that point, and then I'll ask you to go a little bit further. So slowly, set up the table again, put the values in, change the grams to moles, stop there, and then we'll see if you're on the right track. Okay, so I'm going to give you 4 minutes to do that. Right. So I've got it on the board there now. I've written down the equation. I've set up the table. I've put in the values, and I have calculated. I've looked at my 138.6, and it was grams, and I turned it into moles, and it was CCl4, and I turned it into moles at equilibrium. Okay, so our next step is to go into the column that has two pieces of information, and we're going to use green now. And what happens is I had nothing, I produced 0,9, I must have made 0,9. Okay, so I look at my mole ratio and I see it's 1 is to 1 is to 1 and is to 3. Okay, so if I produce 0,9, I must have used 0,9 over there because that's 1 is to 1. I must have produced 0,9 here as well, and that's 1 is to 1. And because that's 1 is to 3, I must have used 2,7 over there. Okay, and now I'm ready to do all my calculations, and I do my calculations and I see that 1,2 minus 0,9 is 0,3, so that's what I have left over at equilibrium. 4 minus 2,7 is 1,3, that's what I have left over at equilibrium. I add 0, I produce 0,9, I now have 0,9. Right, now I need concentrations, and concentration is moles over volume, and I notice the volume that I had, the volume that I had is 2 decimeters cubed. Here's my volume, 2 decimeters cubed. Okay, so concentration is moles over volume. So quite easily, I can look at my 0,3 divided by 2, and I get 0,15. And we don't have to do all those, we can do the rest of that in our heads. That is 0,45 when we divide by 2, that is 0,45, and that is 0,65. Okay, so we've completed the table, and now we need to set up our equilibrium expression. Remember, it's the product of the products. So I've got two products. I've got S2, so it's the concentration of S2Cl2 times the concentration of CCl4 divided by the concentration of CS2 times the concentration of Cl2, and that 3 means it's 3Cl2, so it's Cl2 times Cl2 times Cl2, which means it's cubed. And now we just plug our values in. The concentration of the C2Cl2 is 0,45 multiplied by CCl4 is 0,45 divided by CS2 0,15 multiplied by Cl2 0,65 cubed. And we plug that into our calculator and we have our equilibrium constant. Right, so that gives us 0.45 times 0.45 divided by 0.15 times 0.65 cubed equals 4,92. That's a pretty decent Kc value for that particular chemical engineer as well. it is a value greater than 1, which means the concentration of products is much greater than the concentration of reactants. So that's absolutely wonderful. Absolutely wonderful. So the first two problems was, standard, not easy, but relatively standard problems. And then the next two is, the one is a little bit more difficult, and then the last one is even a little bit more difficult. Right. So, what we're going to do is I'm going to do number 3 for you, because there's a couple of things that I want to show you if there's an unknown amount, and I want to chat about that as well. Okay. Right, so I'm just going to give you an opportunity just to take all of that down, just give you about 30 more seconds to take that down. The power outages has just started in our area. The power outages has just started in our area, but don't worry, I've got a UPS and we can continue until 4:15. It's not a problem. Right. I'm going to erase this one and do number 3 below here. Right, the next problem is slightly different. And what we're going to do is we're going to go through it exactly in the same way, and we're going to then follow through using the same method. And there's just a couple of things that I want you to take note of, and a couple of things that I want you to pick up on. This is regarded as a relatively difficult example, but they quite often ask an unknown value. Right, they quite often ask an unknown value. Somebody said that they were not done. It's a pity. I wanted to do this particular problem today with you to teach you that. I'm sorry that I took it off too early, but I did give you a lot of time to set up the whole problem. So, I'll try and go a little bit slower so that you have enough time to write. I'm sorry that some of you did not have enough time to write. I take note of your exception. Right, so I'm going to write nitrogen plus 3 hydrogen goes to 2 ammonia. And we write that so that we can see the mole ratio. So we're going to have moles at start plus minus moles at equilibrium and concentration at equilibrium. Right, so let me just remove that, write that a little bit higher. Right, so there we go. Nitrogen, hydrogen and ammonia. Let me just write the equation down there. Nitrogen plus 3 hydrogen gives 2 ammonia. And we can look at that again when we need to. Right. So, when we look at this problem, the reaction is investigated on a small scale in the laboratory. Initially 4 moles of nitrogen, an unknown mass of hydrogen. So I'm not going to worry about my unknown mass because we don't have mass in there. So if there's an unknown mass, what I do is I indicate that with an N. Because N is for moles. It's sealed in a 2 decimeter cube container. So 4 moles of nitrogen and an unknown mass X, which is in moles, is sealed in a container. There is no ammonia. At equilibrium, the concentration of the ammonia present in the flask is 1,5 decimeters cubed. So that's 1,5 decimeters cubed. Okay? Notice it is a 2 decimeter cubed container. And since concentration is moles over volume, okay, to get the 1,5 dividing by 2, right, my number of moles, as you can see, 2 times 3 is 2 times 1,5 is 3. So at equilibrium, I had 3 moles of ammonia. That means, according to my equation, the ratio being 1 is to 3, 1 is to 3 is to 2, I'm going to use that ratio over there. So if I continue in that column, and that is where my plus minus is, and that is where I'm going to use the ratio. I had naught, at equilibrium I have 3, I must have made 3. Right. The ratio of ammonia to nitrogen is 2:1. 2:1, there's a 1 there. So if I'm making 3, I must have used 1,5. The ratio of ammonia to hydrogen is 2:3. So if I made 3, I must have used 4,5. That means that with the nitrogen, I had 4 at the start, I used 1,5, which means I have 2,5 left over. And that's my moles at equilibrium. I had N, I used 4,5, and that means I've got N minus 4,5 left over. Since the volume is 2, I use the moles and I divide by 2 to get the concentration. So that is 1,25, and that is N minus 4,5 divided by 2. Now when we set up our Kc, we notice that our equilibrium expression, that is products, and there are 2 of it, so it's squared. These are reactants. There's 3 hydrogens, so it's cubed. Now, this is the advice I have for you. In this particular problem, we had to work backwards they want us to calculate x. They've given us the equilibrium constant. In other words, this value is 1,8. So what I suggest is that n minus 4,5 divided by 2 cubed, we don't do that. We do not sub this in. What we do is we go to our NH3. We've got 1,5 squared. We go to our nitrogen. I've got 1,25. And I'm going to leave this as the concentration of hydrogen cubed. And I'm going to solve this. And when I solve this, I find that the concentration of hydrogen cubed is equal to 1,5 squared divided by 1,25 times 1,8, and put that into the calculator, and I get 1. And that means if that H2 cubed is 1, then the concentration of the hydrogen is also just 1. The wonderful thing about that is that if I put that in there, I was going to get a complicated cubic equation and etc. But now, if I just used it like this and I calculated my concentration, I can just say that the concentration of H2 is equal to n minus 4,5 divided by 2, and that is equal to 1. Which means n minus 4,5 is equal to 2, and n is equal to 6,5 moles. Now I know that this number of moles that was originally put in the sealed container is 6,5. This number of moles that was originally put into the container is 6,5. But remember, we wanted mass. And in particular, the mass of hydrogen. We now know the number of moles. And mass is equal to moles times the molar mass. So I've got 6,5 moles times 2, and I get 13 grams. Right. So there's another problem that's on the next page, and you can try that problem yourself, and you can ask your teacher to do it with you. So I've shown you two very basic or standard KC calculations that came directly out of examinations. All these questions comes out of past examination papers. And then I've showed you a rather more complicated one where we had to do it in reverse. The advice there is, if there is a column which has unknown values in it, then do not substitute that concentration with the fraction and the unknown value, because the equation gets really complicated. Just leave that as the concentration of that particular column, and then what then happens is your calculation becomes much easier, as can be seen over here. I can just imagine what it would have looked like if we substituted n minus 4,5 divided by 2 all cubed, and we got a cubic equation, and yeah, you would have panicked. So do not substitute that in. That is my advice to you. Take note of the color code. The color code, you just have to use the first few examples that you do. After that, you get used to the table, and you don't have to use the color code anymore. The color code is just there to assist you to see what information was given, where did I use the ratio, and that you use the ratio always in that plus minus column. I hope you learned something today again. I will be back next week, and I will spend my time explaining the Chatelier's principle, unless I ask some of the teachers to contact me and tell me, and ask and suggest what I cover next week, just contact me tomorrow or Monday, and then I can set up a worksheet and we can go from there. So thank you very much. I hope you enjoyed it as much as I did. I'm trying to go slower. I will try much harder next week to go a little bit slower. I'm also talking to you, giving you an opportunity to write things down, and I will see you next week. So I'll give you another 2 minutes so that you can write it down, and then I'm going to sign off. Bye-bye.
Thank you very much indeed, Graham. Fantastic lesson. Everybody, I've got recordings come to you guys later, so let you know where it is. Cheers.